Hello students, today we are going to learn how to find the electric field due to a plane sheet using Gauss theorem. In the last class, if you remember, we learned how to find the electric field due to a straight, long, infinitely charged conductor. So today let's see how we are doing it. So see, this is a plane sheet and my aim is to find the electric field at a point P here due to this plane sheet. So if you remember, whenever we are using Gauss theorem, we will follow some steps. So first thing is we will consider a Gaussian surface. So here also I am going to consider a Gaussian surface. And if you remember, that surface should pass through the particular point. So I am going to consider a cylinder only, but little different in this manner. If you remember, last class we considered the surface like this, right? So but today I am considering in this manner. Okay. And if you see this plane sheet, it is like this. So all the positive charges are distributed all over the surface. So when the charges are distributed on a surface, if you remember how we will represent charge Q is equal to sigma into A. If you remember, we have learned surface charge density is Q by A. And from that we will get Q is equal to sigma into A. Remember this. Okay. So first point, I should mention what Gaussian surface I'm considering. So I'm here considering a cylindrical Gaussian surface. Fine. Next, this Gaussian surface can be split into three parts. If you see, this is the cylinder that I have considered. And let's say this is curved part, that is 1. And this is 1 and 2. And this is the other end 3. And since this is a plane sheet and the charges are everywhere like this, so electric field will be directed outwards like this. Okay, here also. So this is how the electric field is and this is how my surface is. Okay, now let's see how we are going to find E dot ds, right? So the same thing that we did in the last class, we are going to do in this situation also. So let's start. So point number 2, we will find closed integral E dot ds, that is nothing but integral E ds cos theta in surface 1. So again I'm telling, see, okay, I will draw in the same method that we have taken so that it is not confusing. So like this we have taken the cylinder, right? Okay, so this is surface 1, this is 2 and this is 3. So the electric flux, that is integral phi dot ds due to this whole surface is nothing but E dot ds due to 1 plus E dot ds due to 2 plus 3. So that only I have written here, 2 into EDS, or I will just simply write E dot ds because otherwise I have to again use cos theta 1, theta 2 and so on. So we will write this. So this is plus for surface 2 E dot ds plus for surface 3 E dot ds. Okay. Now let's see. For surface 1, I'm doing it separately. E dot ds is nothing but EDS cos theta. Now let's see what is this theta. If you see here, always I have said, if you consider any surface, what is area vector? Perpendicular. That is normal to it. So if I consider this surface now, what is area vector direction? It is in this direction, correct? Perpendicular, because I have taken the surface like this. So this is the area vector. But what is the direction of electric field? Just now I said you, direction of electric field is like this, right? Okay. So what is theta? Theta is equal to 90 degree. So in this case, theta is equal to 90 degree. Therefore, cos 90 is how much? 0. So this will be 0. So I am entering this value here. So this is 0. Okay. Plus, let's see for surface 2. So this is my surface 2. And here is a plane sheet and electric field here. Due to this, it is directed like this. Okay. What about my area vector? If you see only 2, if I draw here, this is the normal and the electric field is this direction. So what is theta? Theta is equal to 0 degree. Correct? So if I write for surface 2, it will be E ds cos 0, that is nothing but integral E ds. Clear? So here I have to write this as E ds plus, similarly for surface 3, if you see, this is E and this is area vector. So again theta will be equal to 0 degree. So as before, we will again get this to be E ds. Clear? So finally, what we have got is integral E dot ds is equal to E ds plus E ds. Okay. Now, see, this is my Gaussian surface, right? Okay, let's take, this is the plane sheet and this is the point P. Let us take the radius to be R, okay? And I am considering that the whole area of this end is A, okay? Similarly, this will also have the same area A, right? Because this is a cylinder and both will have the same area. This part alone if I cut and take, right? So, this is nothing but E into integral ds plus E into integral ds. Just now I said the whole area I am taking as A. So I have to write this as E into A plus E into A, which will be nothing but 2 into EA, right? And we already know this integral E dot ds is nothing but 5. These steps are standard for all the derivations. If you see, we will do the same steps. First, we will define our Gaussian surface. Number 2, we will find E dot ds. And from the surface, we will divide that surface into 2 or 3 more surfaces. And we will find E dot ds for everything. Finally, we will tell that E dot ds is nothing but flux. Okay. Next, using Gauss theorem, what do we know? Using Gauss theorem, we know that phi E, that is electric flux, is equal to Q by epsilon naught. And since this Q is not a point, it is distributed all over the surface like this. Here, 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 everywhere Q is distributed. So I will use sigma A instead of Q. Okay. So here I have to write sigma A by epsilon naught. Already I have said why we will use this. Okay. So this is equation 2. If you see equation 1 and 2, LHS are same. So we can equate the RHS. So equating 1 and 2, what we will get is 2 into EA is equal to sigma A by epsilon naught. So A and A will get cancelled. So my final expression will be sigma by 2 epsilon naught. Okay. So this is the final expression for electric field due to the plane sheet. Now, next I have to specify the direction. So when I write E vector, it is nothing but sigma by 2 epsilon naught into n cap. I have already said what is this n cap. N cap is nothing but a unit vector which describes or defines the direction of electric field. And as we discussed before, the same thing. If sigma is positive, then electric field will be directed outwards. See, if you have not seen the previous video, then you will be confused. See that, then you will understand how I am writing this. Okay. So when sigma is positive, that means charge is positive. So electric field will be directed outwards. Similarly, if sigma is negative, then electric field will be directed inwards. Okay. So this is a next important derivation we have done based on Gauss theorem. So I will just tell you once more so that you understand it better. So listen. So our aim is to find what is the electric field. So this area is A, I will mark it. Okay. So our aim is to find electric field at some point P due to this plane sheet. Okay, so for that I am considering a Gaussian surface. What is the shape? It is a cylindrical Gaussian surface. Let's take this as surface 1, surface 2 and surface 3. Okay, so in this cylindrical Gaussian surface, I am dividing the surface into 3 parts. Number 1 is the curved part and number 2 is this end and number 3 is this end. Okay, so next step I am finding what is E dot ds. So I have to add all the 3 parts. So I have added this, this and this, and separately I am finding, since it is E dot ds, I should find what is E ds cos theta. So I am finding, if you see for the curved part, theta is equal to 90 degree. So we get 0. But for both 2 and 3, we are getting theta is equal to 0. So we end up like this. Then if we take the whole area of this part to be A and this part to be A, and if we substitute, I will get here EA plus EA, and that will be nothing but 2 into EA. So finally my flux that I got is 2 into EA. But using Gauss theorem, I know electric flux is nothing but Q by epsilon naught. But this Q is not a point charge here. Since it is distributed all over the surface, I am writing it as sigma A by epsilon naught. Where what is sigma? Sigma is nothing but surface charge density. Okay. Now, equating 1 and 2, we finally get the electric field is sigma by 2 epsilon naught. This is the magnitude. What about direction? Suppose if sigma is positive, then it will be directed outwards. Suppose if sigma is negative, then it will be directed inwards. To show direction, I am just multiplying it by a unit vector n cap. So the final expression is sigma by 2 epsilon naught into n cap. Right? I hope it is clear. Next, we are going to find electric field due to charged sphere. Okay, using Gauss theorem. So due to charged sphere, here we are going to take two cases. So in this, I will be going little fast because you already know the steps, so you can follow it easier. So see here, this is a sphere I have considered, and let's say my aim is to find what is the electric field at a point P here. Okay, and this is infinitely charged sphere. Fine. So for this, first what we have to do? We have to consider a Gaussian surface. So see here, this is a Gaussian surface that I have considered. And let this radius be capital R and let this radius be smaller. So if you see any point, if you consider also, this radius is same. So my Gaussian surface is correct. So what Gaussian surface I have considered? I have considered a spherical Gaussian surface. Okay. Spherical Gaussian surface, and the point P is lying on the surface, right? And let R be the radius of the spherical Gaussian surface. Okay. And what is capital R? Capital R is the radius of the conductor. Okay. Now, next what we have to do? We have to find E dot ds. So shall we find? So what is closed integral E dot ds? It is equal to integral E ds cos theta. Okay, let's find this. What is theta? If you see, this is the surface. So already I have said it will be directed out to normally like this. And what is the direction of electric field? It is also like this. So what about theta? Theta will be equal to 0 degrees. So since theta is equal to 0 degree, I can write this as integral E ds. And since R is constant, I can take E out. So it will be integral ds. That is nothing but the surface area is 4 pi r square. So finally, I got integral E dot ds is nothing but E into 4 pi r square. Next step is, this is actually step 2, right? We are finding E dot ds. Step 3, using Gauss theorem, I know phi is equal to Q by epsilon naught. This is also nothing but phi is equal to E into 4 pi r square. How I am writing this? Already we have been doing the same thing, right? Phi E by definition is E dot ds. So I am writing like this. Okay. Equation 1. This is equation 2. So step 4, I have to equate both. If you equate both, what you will get? E into 4 pi r square is equal to Q by epsilon naught. So what is E? E is equal to Q by 4 pi r square epsilon naught. Here also you can ask, ma'am, it is a sphere, so the charges will be distributed everywhere. So how we can use Q? So here also instead of Q, you have to write as sigma. Okay, I'll write in the next page for you. So E will be equal to sigma A by 4 pi epsilon naught r square. Here again, what is 4 pi r square? It is nothing but surface area. So it will be sigma A by A into epsilon naught. A and A, if it gets cancelled, you will be left with sigma by epsilon naught. So this is the electric field we have found due to a point that is lying outside a charged sphere. So what we did, to find the electric field at some point which is lying outside a charged sphere, we considered a spherical Gaussian surface. And we have defined some important things like what is the radius of the surface and what is the radius of the sphere. Okay. Next step, we have found what is E dot ds. So if you see here, E dot ds is nothing but E ds cos theta. Here theta, if you see, this is the area vector direction and this is the electric field direction. Theta is 0. So if we substitute theta is equal to 0, we will get cos 0 is 1. So this will become E ds. Now E is a constant, so bringing it out, I will get E into integral ds. Surface area is nothing but we already know by formula it is 4 pi r square. So I have substituted here. And we also know that this integral E dot ds is nothing but flux phi. So I have written this here. Okay. Next, using Gauss theorem. This is using Gauss theorem. You have to write one line. Okay. So using Gauss theorem, we know that phi is equal to q by epsilon naught. So if I see equation 1 and 2, LHS is same. So I am equating the RHS. And since it is not distributed in only one point, it is distributed uniformly throughout the conductor. So I am using the term sigma. Okay. So instead of Q, I am going to use sigma into A. So if I use it, I will get this. And after taking this and doing some small multiplications, some small mathematics, I will finally arrive at E is equal to sigma by epsilon naught. Here again, if I have to write what is E vector, it will be nothing but E vector is equal to sigma by epsilon naught dot n cap. Okay. So this is electric field at a point outside uniformly charged conductor, spherical conductor. Next, I am going to find, see carefully, this is again uniformly charged sphere, but now my aim is to find the electric field somewhere here. Last time we found here, right? So now let me say the point P is here and this is the center. Okay. So in this case also, first I am going to consider a spherical Gaussian surface only. So here also the shape of my Gaussian surface is spherical. But see where I am going to consider. If you see the previous case, I have considered the Gaussian surface to be a spherical Gaussian surface, but it is outside the sphere because the point was lying outside the sphere, right? But here I am going to consider spherical Gaussian surface inside the sphere. So see how I am going to draw that. This is my spherical Gaussian surface. Okay, right. And this is radius r and this is radius r. So small r, I am using it for representing the radius of Gaussian surface. Gaussian surface, and capital R is the radius of the spherical conductor. So our first job is done. We have defined what is the Gaussian surface. Number 2, what we will do, we will find integral E dot ds. So let's do it. So integral E dot ds will be nothing but integral E ds cos theta. And if you see here, what is the area vector? Area vector will be in this direction, as well as electric field will be also directed outwards. So it will be as before, it will be E into 4 pi r square. Okay. Now, what is by Gauss theorem? Phi E is equal to Q by epsilon naught. But let's see one thing. See, you should know this is a very important thing, but you will learn in detail about this in the second lesson. But now know this fact. Suppose I'm charging any sphere, okay? So this is a sphere. So see, I'll draw it here. This is a sphere. And I am charging the sphere. What is the meaning of that? Either I can give more electrons or I can take away. So however, whenever I charge a sphere, when I give excess amount of charges to it, no charges will reside inside the sphere. You may ask why. You will learn about this in detail in your second lesson. Okay. But now know this important, very, very important fact that when we provide charges to any conductor, the charges will reside only on the surface of the conductor like this. Suppose I am providing positive charges. That means what? I'm taking away electrons. Okay. So that time the charges will not be here. It will not get accumulated inside the conductor. Inside the conductor, always net charge will be 0. You should know this. I'm talking about net charge. So always inside a conductor, net charge is 0. the charges will reside only on the surface. So if I consider only here, if you remember in all the other cases, I am taking a conductor and I consider the point P here. In second case, if you remember, I consider a plane sheet, but I consider the point outside. The third case also, when I took a sphere, the point was outside, but only here I am taking the point to be inside. So whenever the point is inside the conductor, you should know net charge inside the conductor is 0. So keeping that fact in mind, so here this charge is nothing but 0 because no charges reside inside. Since Q is equal to 0 inside the Gaussian surface. So always if you see, my Gaussian surface was lying outside the conductor, right? But here the Gaussian surface is inside, and I know inside the net charge is 0. So this Q is nothing but, if you see the definition for Gauss law, it is the charges that are enclosed inside the surface. Charges enclosed inside the surface. So here inside the surface charge is 0. So I have to write this as 0. Okay. This is equation 2 and this is equation 1. Equating 1 and 2, what we will get? E into 4 pi r square is equal to 0. Therefore, E is equal to 0. Remember this. This is an important 1 mark question also. What is the electric field inside a charged conductor? It can be a sphere or anything. Always electric field inside is 0 because net charge inside a conductor is 0. If we provide charges, it will be distributed only on the outside or the surface of the conductor, but always inside net charge is 0. Okay. So using Gauss theorem, we have learned important derivations. Number 1, due to a long infinite conductor. Number 2, due to a plane sheet. And number 3, due to a sphere when the point lies outside. And number 4 is when the point lies inside. So you can, like, all of these are important 5 mark questions. So you have to be thorough, but the method is very simple. Once you learn how to do, it is very easy for you. You can do by yourself. Okay. So with this, mostly I'm thinking our first lesson is at the end. We have to solve some problems. So I will just give the problem list to you. You can write that questions and keep, and we will solve in the next class. Thank you.